tides. It's very hard to compete with iron tides these days. So thank you for coming. So I will be I will be talking about joint work with my group. So you on Karlström, Julian Karov, they were involved in the part on Superconductivity theory, and Mikhail Silayev was responsible for microscopic theory. So these are great guys who did all the heavy lifting. And all right. So this is type 1. So I will try to present for your considerations an argument on classification that current classifications of superconductors in type 1 and type 2 is insufficient. And I will present this argument in two stages. One of them will be what I think is clear cut of a system which falls outside type 2, type 1, type 2 dichotomy. And I will also try to argue how what is the scope of a system which can violate type 1, type 2 dichotomy. All right. So the idea of type 1.5 superconductivity is very simple, can be written in one line. So if you have multi-component systems, in general, you'll have several coherence links. And there is no fundamental reason which can prohibit occurrence of a situation where one coherence length is smaller than penetration length of magnetic field, and another coherence length is larger than magnetic field penetration length. And it was termed by Viktor Mashalkov as type 1.5 superconductivity. So let us consider a simple mixture of two superconducting condensates. So the minimal model is the Ginsburg-Landau model. This is the standard Ginsburg-Landau model where the fields, the complex fields, are replicated twice. So there is a lot of history behind two-component Ginsburg-Landau models. So these are two band superconductors. Then one can have certain states triplet superconductors where you have multiple components. And for a long time it was also discussed in the context of neutron stars, where two condensates represent protonic Hooker pairs and sigma minus Gigeronic Hooker pairs, and sigma minus Gigerons are extremely stable in neutron stars for a very long lifetime at these pressures. So these are two condensates, which in case of, let's say, protons and Gigerons, the model becomes even simpler because of then these terms, this kind of couplings between the condensates, they are forbidden on symmetry grounds. So another system where you have condensates which are not coupled by intercomponent Josephson interaction is a projected unitarity states of hydrogen, which we also discussed since London. And in that case, you have electronic Hooker pairs, protonic Hooker pairs, and since you cannot convert electrons to protons, you have intercomponent Josephson terms strictly forbidden on symmetry grounds. And then your condensates are coupled only through vector potential. There could be also some different kind of couplings, but like anti-Hilbert coupling, but no intercomponent Josephson coupling. And let me start with considering first this simplest region, and there view that there is no type 1 and type 2 dichotomy in that case. So first of all, what is a vortex excitation in that case? If you have components which are talking to each other through coupling to the same vector potential. So in that case, even though there is no other coupling, there is only one kind of vortex excitation which can form an external magnetic field. And it can be seen as follows. First, let us take the London limit in this two-component model, and let us just extract from our two-component London models model gradient of the phase difference. So in that case, we extract gradient of the phase difference. So these are phases of the complex stellar fields. So in that case, you can recognize something like a gradient term for Gross-Pitayevsky equation. There is no coupling to vector potential in this combination of the fields. And that means if you calculate, if you try to set up a vortex with space binding only in one component, then this vortex will have logarithmically divergent energy, similar like a vortex in a Gross-Pilaevsky energy, in Gross-Pilaevsky function. So, and then in that case, if you calculate magnetic flux carried by elementary vortex, it will be only a fraction of the class quantum, and it will come with logarithmically divergent energy. But if you wind both phases by 2 pi, then this term will be cancelled out. So, and this is the only way to construct a vortex which has finite energy per unit length in this model. So the only thing, the only kind of order excitation, so you can form an external field, even it will have both phases winding by 2 pi, even though there is no intercomponent Josephson coupling. And then, if we have just U1 cross U1 symmetry, if we have no intercomponent Josephson, then you define two Caginus lengths in standard way. We actually like, instead of using Caginus lengths, we like to use inverse of Caginus lengths mu A, and spin iteration lengths, we also like to use inverse iteration lengths mu A. So what follows, mu will be inverse of Caginus lengths and iteration lengths. So, okay, if we have two components now, there's no direct coupling, the Caginus lengths are defined the same way as you find in Tinkham, and there are two of them, and you cannot form like this Superconductivity parameter, just more degrees of freedom. So, and then you can, even by enumerating degrees of freedom, you cannot have type 1, type 2 dichotomy system. So, what then the question to ask, what, oh, yeah, so, as before I go to the next section. So then the vortices, so if you have two different Caginus lengths, there is nothing fundamental which can prohibit this type 1.5 region, one Caginus iteration depth running in between two Caginus lengths. And then if you then your vortex will have two cores. And if these are very different, then one core will be very large, so this is core on psi 2, this is core on psi 1, very small, and the magnetic field falls somewhere in between. And then, if you take two such vortices as shown on this picture, and if you start bringing them together from a long distance, they will feel each other first by their cores, and core-core interaction is attractive. And when they get closer, they start feeling magnetic field of each other, and magnetic field interaction is repulsive. Thus, the interaction potential is long-range attractive, short-range repulsive. So let me, then correspondingly, the phase diagram in general will acquire additional phase where vortices clump together because of this long-range attractive interaction, and to find sample, the system has Meissner state in low magnetic field. It has vortices when you have very high magnetic field, and in between it allows a macroscopic phase separation. Find a sample, macroscopic phase separation in the domain of Meissner and vortex states. All right. So what happens now if we consider two band superconductors? The difference is that two band superconductors, interband interaction always breaks symmetry down to simple U1 symmetry. And that means that there are a lot of terms which are allowed by symmetry, such as intercomponent Josephson coupling, that you have interband period scattering, you have mixed gradient terms of this form, and you can have other terms. So, and the question is how we define Caginus lengths in that case. And there is a lot of misunderstanding in literature how to define Caginus lengths in two-band superconductors. Even outside the type 1.5 discussion, so there is one important thing which is frequently missed, that once you have this kind of couplings, you cannot attribute Caginus lengths directly to gap 1, gap 1, and gap 2. And it follow, it is a bit slow, so we'll skip some slides. So, so let me just retain only one interband coupling, the Josephson coupling. So we have U1 cross U1 system, and then we add intercomponent Josephson coupling. And let me go through the simple case to show how coherence length should be defined in this case. So then, the trivial effect of interband Josephson coupling is that it renormalizes ground state densities. I can calculate it per turbo equilibrium. And it renormalizes magnetic field interaction length. So these are inverse magnetic field interaction length. But it does one radical change also, in addition to this step. So if you now take your original condensates and you calculate the asymptotics away from the vortex core, then if you do careful calculation, you will find that the asymptotic of the field 1 and field 2 will be the same at very long distances, no matter how small is your Josephson coupling. That's one thing. But the other thing is that both fields, they will have contributions in the asymptotical test with two different characteristic exponents. So you can represent them as two basic functions. So this inverse coherence length 1, inverse coherence length 2. So we didn't define what it is, but just so far define it shortly. And they will come, the different exponents in each field, they will come with different prefactors, which we will call mixing angle. We can parameterize with some angle theta. So this is basic function, this is exponents. However, so if we redefine our fields, representing them as linear combinations of our original fields, we can find always two linear combinations, each behaving according to a single exponential law. So it can be also, so if you try to set up some equivalent of how a coherence length is defined in Tinkham in single band superconductor, if we try to do the same procedure here, so we should linearize our theory around the ground state. Let's write linearized two-component theory for small perturbations of fields around the ground state is simplified. And then going to some representation in linear combinations of the original fields, we can always decouple the linearized theory into two decoupled equations. And it will give exactly the same kind of intervortex interactions as in U1 cross U1 theory, except one difference, except the difference is that now our coherence lengths cannot be attributed directly to gap 1 and gap 2, but they can be attributed to linear combinations.